We spent a bit of time reviewing principles of enzymes that obey Michaelis-Menten kinetics. We now want to turn our attention to allosteric enzymes and examine one example in greater detail. The term allosteric literally means other shape and indicates a case where a protein may adopt more than one shape. Allosteric enzymes are usually multi-subunit complexes and are influenced by other compounds. The binding of these effectors results in a change in the quaternary structure of the enzyme. They serve to either enhance or diminish their native activity. Aspartate transcarbamylase, or ATCase, is perhaps the most prominent example of an allosteric enzyme, and its quaternary structure is illustrated below. It is also a good example of an enzyme that participates in feedback inhibition. A key point in understanding this subject is to realize that Michaelis-Menten enzymes and allosteric enzymes behave very differently in response to inhibitors. Here we see illustrated the reaction catalyzed by ATCase, the condensation of aspartate and carboyl phosphate to form carboyl aspartate. This is the committed step in pyrimidine biosynthesis and is a key regulatory point. Recall that in feedback inhibition, an end product of the pathway builds and feeds back to an earlier step in the pathway to inhibit the enzyme that catalyzes that step. The logic of this arrangement is that product can only build if it is not being utilized. If that is the case, then why waste resources by making more? From our studies of hemoglobin, you will recall that a sigmoidal binding plot was indicative of allostery, of cooperativity in binding. We find the same type of curve in substrate saturation curves for allosteric enzymes, as shown here. It suggests that the enzyme can adopt two different conformations, one that predominates at low substrate concentrations, the low affinity form, and then as substrate concentration increases, it adopts a higher affinity conformation. For enzymes that have two substrates, like ATCase, we hold one substrate concentration constant and vary the other. In the graph here, the blue curve represents the control, ATCase activity in the absence of any effectors. This represents its native activity. Notice that it is still sigmoidal. Notice what happens if the same experiment is conducted in the presence of CTP, the black curve. The curve becomes more sigmoidal, so activity is even more cooperative. It has also shifted right, thereby demonstrating reduced affinity for substrate. This represents the influence of an allosteric inhibitor. In contrast, look at the pink curve, representing the influence of ATP on ATCase activity. Notice that it has become more hyperbolic. That is, activity is less cooperative dependent. It has also shifted left, indicating a higher affinity of substrate binding. This represents the influence of an allosteric activator. Now let's examine the quaternary structure in order to understand these outcomes. ATCase has a set of two catalytic trimers, pictured here in green, which contain the active sites where the enzymatic reactions occur. It also contains three regulatory dimers in brown. The regulatory subunits are where the allosteric effectors bind. Catalysis is dependent on the catalytic subunits but independent of the regulatory subunits. However, without the R subunits, the enzyme loses all allosteric regulations. It is the distinct quaternary structure that relates to the allosteric behavior of this enzyme.